Episode 10 Hermite Interpolation. Match the value, match the slope, hug the curve. Here's the cubic we know well from the root finding series. X cubed minus x minus 2. Pick 2 points on it. At x equals 1, the value is minus 2. At x equals 2, it's 4. Lagrange gives the straight line through those 2 points. It gets the height right at both points, but it's heading the wrong way. Look at the angle it makes as it cuts through the curve. What if we also matched the slope at each point? The true slopes there are 2 and 11. Match value and slope at both points, and the fit becomes a cubic. And here it's exact. It sits right on the curve. It hugs. Same points, but now the fit leaves each one heading the right way. 2 points, and at each one we now fix 2 things, the value and the slope. Count them: 1, 2, 3, 4. 4 conditions. A cubic has exactly 4 coefficients, 4 conditions, 4 unknowns. That points down exactly 1 cubic. Value plus slope at each point. That's what pins it down. Same as the last episode, the divided difference board, with one new rule. Here's our data. At x equals 1, value minus 2, slope is 2. At x equals 2, value 4, slope 11. Now the new rule. Each point goes into the table twice. So 1 with its value minus 2, and 1 again, minus 2 again. The usual difference here would be 0 over 0, a point with itself. That repeated entry is asking for the derivative. So the slope goes in, that is 2. Next line, 2 with its value 4. The ordinary difference works here. 4 minus 2 over 2 minus 1 is 6. Then the second difference. 6 minus 2 over 2 minus 1, it is 4. Same story for 2 listed twice. Its slope drops straight in, 11. 11 minus 6 is 5. And the top of the table, 5 minus 4 over 2 minus 1, 1. Read off the leading diagonal. Minus 2, 2, 4, 1. Those are the coefficients. Newton form straight off that diagonal. H of x is minus 2 plus 2 times x minus 1 plus 4 times x minus 1 squared plus x minus 1 squared times x minus 2. Multiply it out and it collapses to x cubed minus x minus 2. We fed in a cubic and Hermite handed it straight back. Hold on to that. Why does matching slopes by tangency? Look at the fit's building blocks. Each point contributes its factor squared. Compare the two shapes. A single root just crosses. It goes through the axis at an angle. A double root touches and turns. It lands flat. The value is 0 and the slope is 0 too. So the fit doesn't just touch the value at each point. Its slope matches too. That is tangency. That's the hugging picture from the start. The fit kisses the curve at every point, the osculating polynomial. Now the real reason Hermite exists. This data is from the book 3 tabulated points. Numbers we measured, no formula in sight. At 1.3, value 0.62000860, slope minus 0.52202232. At 1.6, value 0.45544022. Slope is minus 0.5698959. And at 1.9, value is 0.2818186 and slope is minus 0.5811571. 3 points, each listed twice. A 6-row table. First row 1.3, value 0.62000860. 1.3 again, and the repeated point takes its slope minus 0.5220232. 1.6 value 0.4554022. The ordinary difference here is minus 0.5489460, and the difference of the differences minus 0.08974,267. 1.6 again, its slope drops in minus 0.5698959. Carry the columns across minus 0.069830, then 0.066365556. 1.9 value 0.2818186. Its difference minus 0.5786120. Across again minus 0.0290537, then 0.067965556 and 0.0026666. Last pair 1.9 twice, slope minus 0.5811571. Write the row out minus 0.0084837, 0.06856667, 0.001001852, and the last one minus 0.002774691. The leading diagonal is the whole answer. Those 6 numbers are the coefficients. Evaluate at 1.5 term by term. The first term is the value itself 0.6200860. The slope term minus 0.5220232 times 0.2 minus 0.10444046. The next term minus 0.0035897. Then minus 0.0002655. The last 0.0000011 plus 0.0000004. Add them up. H at 1.5 is 0.5118277. No formula in sight, just 8 numbers of a table, and Hermite gives us the value between them. Tangent accurate. Here's the general machine. N plus 1 points, each listed twice, and the same divided difference sum, now running to degree 2 n plus 1. The z's are just the points, written down twice each. And the error, same shape as before, a high derivative over a factorial. But look at the product on the right. Every factor is squared. Each x minus xi squared is a double root of the error. And a double root means tangency. That's the whole scene 4 picture, sitting inside the formula. One more thing the formula hands us. If f itself is a polynomial of degree at most 2n plus 1, that high derivative is 0. The error vanishes. Hermite gives f back exactly. And that's exactly why our cubic came back. X cubed minus x minus 2 has degree 3, at most 2n plus 1. So Hermite returned it untouched. Time to make it yours. Exercise number 1. A curve starts at height 1 with slope 0 and lands at height 0 with slope 0 at x equals 0 and x equals 1. Build the Hermite cubic through the data and evaluate it at 1/2. Pause here, try it yourself first. You should land on 2x cubed minus 3x squared plus 1 and at 1/2, exactly 1/2. That's the smooth step curve. Exercise 2. You have measured a function at 3 points. Here are the values and the slopes. It's the same data we just ran through the 6-row table. So the coefficients are already yours. Estimate f at 1.4. Pause and give it a go. Writing the same Newton form out at 1.4 gives 0.5668555144. Last one. No arithmetic, just thinking. A polynomial of degree 4 is sampled at 3 points. Values and slopes both. Does the Hermite fit hand that polynomial back exactly? Think about the degree bound before your answer. Yes, 3 points make the fit degree 5 at most, and 4 is at most 5. Reproduction does the rest. So match the value and the slope, and the fit is tangent at every point. And it's the same divided difference machine we already own. Just list each point twice. Next time, one big polynomial can wobble. When one polynomial is not enough, stitch many. So we will discuss about cubic splines. If this helped, subscribe and I'll see you at the splines.